So I have a ton of stuff I need to cover today. And so all I can say is hold on to your hats and glasses, kids, because this is the wildest ride in the wilderness. There's a lot of stuff we're going to cover. So please pay attention. Just want to make sure that I shared my screen. I want to make sure that everything's being shared. Okay, cool. The assignment for today is 1.5. And 1.5 is on exponential and logarithmic functions. Bless you. Exponential and logarithmic. This is a huge idea, lots and lots of stuff. Secondary Math 1 was all about exponents, and you also saw exponents in Secondary Math 2 and 3. Logarithms was last year. In fact, you probably spent a month going over logarithms. So I'm going to be covering several months worth of material in a span of an hour and a half. So all I can do is apologize if it seems too fast to you, but hopefully you will see this as a review. What makes a function exponential? Graphically, actually as an equation. What makes an equation exponential? What's the answer? Brandon.
It has a variable in the exponent.
Yeah, the variable is in the exponent. I agree with you. Yeah. The variable is in the exponent. Brandon, I was going to say the variable is the exponent, but that's not entirely true.
Yeah, because the variable cannot push it.
Yep.
You have like a whole linear or whatever, however much the variable wants out there.
Yep, I agree with you. I actually like yours is more precise than the direction I was going to go. So if I have something like I have my function here is say y equals, and then we have some base. It doesn't matter what the base is. We'll just say for argument's sake that is 2, and then to the power of x. Then Bryn, why is this exponential?
Because the exponent contains a variable.
Yeah, the exponent contains a variable, and so we know that this is exponential. Now, that is as when we write out something algebraically. What makes a graph exponential? What makes a graph exponential? Yes, sir.
That could be very wrong, right? It means it's when it is infinitely approaching something. Could be very wrong.
Okay, so infinitely approaching something, you're not giving me direction. You are right. I just not, if we were going to be more precise in what we are approaching, in fact, more specifically, it's a horizontal approach. There's some value, there's a horizontal line called an asymptote that the graph converges on. It approaches that. So we have to have a horizontal asymptote. Is everybody comfortable with what an asymptote is from last year? An asymptote is an imaginary line that the graph converges on. So if I have, here's my Cartesian grid, and let's say that this is we'll say this is y equals, I don't know, 3, which would mean then that y is always 3 along this line. If I converge on this line, that is one of the characteristics of exponential. So if I curved from the bottom like this, that would be exponential. We could converge from the top, right? I could converge from the top. I could go like this. I could converge from the top on that line. That would also make it exponential. Now, we also have that curve that sharply increases to infinity. That's an important characteristic of an exponential graph. So there's two important parts of an exponential graph. Two important parts. One side curves sharply to a important parts. So one side curves sharply to infinity or negative infinity. And the other side has to have a horizontal asymptote. The other side has a horizontal asymptote. Where's Elaine? Eileen. Eileen, what is an asymptote? It's a value that y can't be. If it's horizontal, that what can be? It y can't be. Y cannot be it, right? So if I have something like this, let's say that, let's do one specifically. Let's do y equals 2x. What value, Eileen, can y not be? Zero. If I make y 0, so I have 0 equals 2 to the power of x, what value can I have for x that will give me 0? Let's plug in some values. Let's plug in, here's x and here's y. Let's plug in -2, -1, 0, 1, and 2. Let's throw in some values. Let's go ahead and let's do Eileen. If I plug in 0 here, what do I get? So if I have 2 to the power of 0, what's our 0 exponent rule? It's always going to be 1. So that's going to give me 1. What if I plug in 1 here? It's 2. What if I plug in 2 here? I get 4. I get 4. What if I plug in -1 here? What's 2 to the power of -1? What's our negative exponent rule? It is 1/2. Yep, we move it to the denominator, we get 1/2. So that's going to give us 1/2. What if I plug in -2? 1/4. What horizontal line are we converging on? Yeah, we can never reach 0. In fact, we'll never get any negative. Y's will never be negative in this case. So we see that we're converging as x becomes more negative, like a smaller and smaller number, then we converge on 0. So we would have in this case a graph that looks something like this. This is our horizontal asymptote at y equals 0, and then our graph is going to look something like this. That would be our exponential growth here. That's an exponential growth. All right, so I want to talk about transformations of an exponential. Let's talk about transformations of an exponential. Let's scroll down here. If you're still writing, please let me know. I don't want to go too fast. So we talked about a graph that's exponential. We talked about an equation that's exponential. Now I want to talk about transformations. Now let's start with something like y equals 2 to the power of x. Now we already graphed it. It looks like something like this. And I guess when x is 0, y is 1, And when x is 1, y is 2. When x is 2, y is 4. And it just shoots off to infinity. Now, is it possible to do a transformation of this graph where we get a vertical reflection? How? Bryn?
-2.
Yeah, if we do something, when we want it vertical, do we do something to the function or in the function? To the function. Remember that 2 versus in. To the function is vertical. And in the function is horizontal. This is super important. And funny business, yes, I should write that. And funny. Spelling it wrong. And funny business. And so if I multiply a negative in the front right here, then that's going to be to the function. We're taking all the function, we're multiplying it by a negative, which is going to give us a vertical reflection. So if I have y equals negative to the power of x, then I'm going to get a graph that looks something like this. Is this still exponential? Does it still follow our two conditions that we have some type of horizontal asymptote and it curves to infinity or negative infinity? Yeah, so this is still exponential. How would I do a horizontal flip? I want to take this graph and I want to do a horizontal flip. Yes.
Would you do 2 to the negative x?
2 to the negative x. Yeah, we're going to do something in the function. We want it to be horizontal. We're going to do something in the function to get a horizontal flip. So I have y equals 2 to the power of negative x, and then that's going to give me a graph that looks something like this. Is this still exponential?
Yeah.
Yeah, in fact, we call this an exponential decay, an exponential growth versus an exponential decay. Radiation, for example, decays in an exponential decay fashion. Also, Newton's law of cooling. When you put something, if you take something off the stove, then the temperature of your soup converges on the ambient temperature or the temperature of the room in an exponential decay fashion. That's really interesting. I didn't learn that until calculus, that we have this idea. It took me, that was after my first master's degree that I learned about this idea of Newton's law of cooling. What? Newton, yeah, it's so cool. And you throw it in, you take your soup and you put it in the refrigerator. The soup will converge on the temperature of the refrigerator. I think that's in an exponential decay fashion. So I guess technically you could argue, based upon Newton's law of cooling, that the soup never reaches the temperature of the refrigerator. It just converges on it. But I suppose you would have to argue with, I mean, that's mathematically, right? But, you know, I don't know. Does it get so close that we say that it's really basically the same temperature? Yes, sir.
Well, technically, without cooling works, it wouldn't ever be able to reach the initial because it would slowly converge together.
Yep. So based upon Newton's law of cooling, if you put a bowl of soup in the refrigerator, based on his law, mathematically, the soup never reaches the temperature of the refrigerator. But it gets so close that you can't tell the difference because it seems so close. Right, what about, how would I do, what if I wanted to shift it? What if I wanted to shift it up or down? What would I do to this? This is my parent, it's called a parent function because everything, all of our transformations are derived from this parent function. What if I want to shift it left or right? What do I do? Yes, sir, Bentley.
You would add something to the function.
Okay, so we're going to do something to the function to go up or down because 2 means vertically. And so we take all of this function and then we just add or subtract something to it. Bentley, if I add, what happens?
If you add, it will go up. If you subtract, it will go down.
Yeah, if my equation, I have 2 to the power of x, and if I add 1 or 2 or 3 or 4, it's going to go up. So we'll do, I don't know, how about 5? Let's do 5. So our graph is going to look something, if I'm going too fast, let me know. So this, what was that called? That line that the graph converges on, what's that called? It's an asymptote. Now that asymptote is also being shifted up. The asymptote is no longer y equals 0. What is it? Y equals what? It's y equals 5. Yep. So we're going to go up 5 units. 1, 2, 3, 4, 5. And then the graph converges on that line. So the graph should look something like this. Yep. What if I want to shift this graph to the right? So we're going back to the parent function. I want to shift the parent function to the right by 5 units. How do I shift? Bryn, how do I shift to the right by 5 units?
You subtract 5 from x.
Yeah, from the x, so it's in the function, right? Yeah. Yeah, so it's part of the exponent. So I'm going to subtract over here. I'm going to subtract a 5. And then we have that funny business, right? Bryn, you've changed my way of teaching. When I teach now, I use the verbiage funny business. And you were first to use that last year when we were online. And I think that was really helpful. So I also call it funny business too when I teach it. So we use
It is funny.
and it's true. It's funny and true. So right here, we have this point here of 0, 1, and that has now been shifted over by 5 units. So that point now is, we'll use a different color. How about purple? 1, 2, 3, 4, 5. And we have that point right here. And so we have our new graph that looks something like this. We have shifted to the right by 5 units. It seems like it would be a shift to the left because it's -5, but we have that. Anytime we do something in the function with these parentheses, then we get this. It's the opposite of what we would expect. So in this case, it's a shift to the right. What if I wanted to stretch it up? What if I wanted to stretch this graph up by, I don't know, a factor of 3? I want all this graph to be, so it's like back here, I want this to be all stretched up by a factor of 3. Yes, sir, Bentley.
Wouldn't you times it by 3?
Yeah, we times what by 3? To the function or in the function?
To the function.
To the function. So I'm going to take this y equals 3 times 2 to the power of x. And so that is going to give me something that is going to be much, in fact, that point here of 0, 1 has now been stretched up to 0, 3. So it should be something like this, a lot steeper. Bentley, isn't this just 6 to the power of x? I hate when Mr. Hall asks me trick questions.
No.
Why not?
Because 6 times multiplying 6.
I agree with you. These are not the same.
Hard to vocalize.
It has to do with one of our laws of exponents. In fact, that's the direction we're going. So let's talk about that, Bentley, first, and then I'll have you explain again. And once we go through all the laws. So I want to know, the question that I have for Bentley is, why is this not the same thing as 6 to the power of x? And I want to go through all of the laws. How many laws are there of exponents? Does anybody know? There are 8. We have 8 laws of exponents. We have 8 laws of exponents. So we have a lot. But you know what? Some of these feel the same. So it shouldn't be overwhelming. So this is not the same. And I'm going to have Bentley answer that later, why that's not the same, once we go through our laws. All right, so we're going to go over laws. Laws of exponents. Now, first, before I talk about laws of exponents, I just want to talk about the definition of an exponent. First, the definition. Now, if I have something like 5 plus 5 plus 5, what's the shorthand way of putting all these together? 3 times 5. We use multiplication to put numbers together, the same number that repeats itself using addition. What if I have 5 times 5 times 5? 5 to the power 3. So the definition of an exponent is it's a shorthand way of writing the multiples when we're looking at a number when it repeats itself using multiplication. So where did all the laws come from? Well, the laws came from patterns, mathematicians. So based on this law, or not the law, but the definition, based on the definition, mathematicians saw patterns. And then they wrote the patterns down. They said, I wonder if these always happen. And now we have proofs for them. In fact, I could, in my other classes, I actually show for each one of these why it works. And I don't have time in this class to do that because we still need to talk about logarithms. So if something is confusing to you, I'd be glad to show you why it works and just tell me while we go through these laws. But otherwise, I'm going to assume that you're okay with it. And we're just going to list all of the laws. The first one, if I have, here's our first one. I have a to the power of b times a to the power of c. What is the law that tells me how to put these together? Yes, sir.
I don't know the name, but I think it's property law.
It doesn't matter what the name is. I just want you to tell me. We add the exponents, yeah. So I have a to the power of b plus c. We just add the exponents. If any of these are confusing, I'd be glad to give you an example of why it works. Otherwise, I'm going to just press on. Number 2, I would argue number 2 is similar to the first one. So yeah, there are 8 laws, but some of these are very similar. So the next one, if I have something like this, I have a to the power of b over a to the power of c. How do I put these together? Yes, sir.
Subtract the exponents.
We subtract the exponents. We subtract. Is it Tate? What's your name? One more time.
Thomas.
Thomas. Okay, Thomas. Thank you, Thomas. Yeah, we are going to subtract the exponents. A to the power of b minus c. Are you guys good with this? Okay. The next one, if I have number 3, if I have a to the power of c times b to the power of c, how can I put these together? Yeah, we just multiply the bases. So I have a times b, and then we keep the exponent the same, c. And actually, it's this one, Bentley, that I want you to look at. I'm going to go back up here and steal this. Why is this not true?
Because 3 doesn't have an exponent, it can't be combined.
It does have an exponent, it has an implied exponent.
It doesn't have the same exponent.
It doesn't have the same exponent. We don't have the same base. If we had the same base, what would we do to the exponents? Add the exponents. We don't have the same base. We don't have the same exponent either, so I can't multiply the bases. What is the exponent, Bentley, for 3?
It's 1.
It's 1, yep. We don't have the same bases. We don't have the same exponent. There's nothing we can do. It's already simplified. There's not, this is not true. There's nothing we can do to simplify it. Okay. Okay. Oops, I don't want to resolve it. All right, so the next one is similar to number 3. If I have the same base and I'm dividing, what do I do? Thomas.
You would divide the bases.
Yeah, divide the bases. A divided by b to the power of c. Yep. Okay, how many more laws of exponents do we have?
4.
We have 4 more. Number 5. Number 5, if I have a to the power of b to the power of c, how do we put those together?
You multiply the exponents.
We multiply. Some students get number 5 confused with number 1. How are 5 and 1 different? Yeah, when we multiply, when we add, But if we look at what we started with, one has two bases and we're multiplying, the other just has one. You guys need an explanation for this one, or are you guys comfortable with this? Good, multiply, okay. We just multiply, I have a to the power b times c. Number six, if this is our zero exponent rule, if I have a to the power 0, that has to equal what? Question.
For the B times C, please, can you make it a different alternation symbol because it honestly looks like BX.
I appreciate that. Yeah, please keep me honest. How about parentheses? Are you okay with that? Okay.
That's what I normally use because it doesn't look like anything else.
Yeah. Or a dot, right? Well, a dot sort of looks like a decimal, huh?
Yeah.
That's the problem with the dot.
It's right, BC.
All right. Yeah, I like that. BC. Yeah. BC.
Yeah.
Okay. A to the power of 0 is what?
1.
1. Unless we have 0 to the power of 0. Are you guys good with this? Why this doesn't work? Or do you want an explanation? Okay. Here's your explanation. Here's your explanation of why 0 to the power of 0 does not work. Consider if I have 0 to the power of, let's do this. Let's do 3 to the power of 0, 2 to the power of 0, 1 to the power of 0, 0 to the power of 0, or 0 to the power of 3, 0 to the power of 2, 0 to the power of 1, and 0 to the power of 0. Consider these patterns. 0 to 3 to the power of 0 is what?
1.
It's 1. Based upon our law, it's 1. Oops, I just saved it and I didn't mean to. Now it's going to waste class time to, okay. That's going to be 1. 2 to the power of 0 is
1.
1. 1 to the power of 0 is
1.
1. If this pattern continues, what should this be? It should be 1. Now let's look at, oops, I meant to do this last one as 0. Okay, nope, not in red. How about black? Okay, 0 to the power of 3 is 0 times 0 times 0, which is
0.
0. 0 to the power of 2 is 0 times 0, which is
0.
0 to the power of 1 is,
0.
if this pattern continues, what should this be?
0.
All right, so this can't be something and nothing at the same time. That doesn't make sense. Because it can't be something and it can't be nothing at the same time, then we call this undefined. 0 to the power of 0 is undefined. 0 to the power of 0 is undefined. Okay, good? How many more laws do we have? 2 more. Okay, moving on. Number 7. I have a to the power of -1. What's our -1 exponent rule?
Put the numerator denominator.
Yep. Or we can write 1 over a to the power of -1, which is,
A to the power of 1. A.
it's just a. Do you need an explanation or are you good with this? We're good? Do you need an explanation why this is true? Or are you good with it? Ready with an explanation if you want it. Okay. All right, so that's our law. Number 8, our last one. Our last law is if I have the square or the bth root of a to the power of c, that is a to the power of Thomas?
A to the power of C over B.
C over B, yep. That is our last law. Our root is always the denominator. The root is always the denominator of our fraction. So if I have, in fact, I don't know if this would help to add this extra step. A to the power of C to the power of 1 over B. Our root is always the denominator. And then we use our, what law was that? Where we multiply our 5th law. We use our 5th law, multiply to get a to the power of C over B. So I don't know if that extra step helps. But we have 8 laws of exponents. These laws are going to, this law especially is helpful in calculus. Make sure we learn that one. Actually, all of them are. When we're talking about calculus, we're dealing with exponents a lot. So all of these laws become are helpful when we do that. Unless you have other questions about this, we are going to be moving on to, not logarithms yet. Okay. You guys are good. How do we simplify? So I want to simplify. I have -4 times x squared times y to the power of 3 times z quantity squared over 6 times x times z to the power of -2. I want to simplify that mess. This x here. Yes. We're multiplying 6x z to the power of -2. Where's Anna? Anna, where do I start with this mess? So there's actually two laws. If I want to get rid of this 2 here, there's 2 laws that I have to do simultaneously. One law, I have to do this one where I have a to the power of b to the power of, a times b to the power of c. And then this one can be expanded how? To a times. So that's one that I'm doing. The other one that I'm doing is this one here where I have a to the power of b to the power of c. What did we do with that one? Times. That's the one, this one students get, a lot of times students get law number 1 and this law mixed up. And Bryn doesn't like that I have a times in there, so I'll get rid of that. So yeah, we have both. We have to do both of these at the same time. Just one more time, make sure that we're not confusing these, Anna. Anna, if I have the same bases and I'm multiplying, then I add the exponents, right? Anna? Now if I have to the power of, I have a to the power of b to the power of c, then I do what? Yep, I multiply. So let's look back here at our problem. And so I have to do both of these at the same time to get rid of this 2. So the -4 becomes what?
16.
Yeah, it becomes 16. Anna, do you agree with that? Okay. Anna, what does, so this, I have 16. Anna, what does this become? Nice. X to the power 4. Oh, 16. Anna, what about this one? Yeah, y to the power, bless you, y to the power 6. Y to the power 6. Okay, what about this one? Bless you. Yeah, z squared. Nice. Z squared. And then in the denominator, we still have this 6xz to the power of -2. Where's Gabby? Gabby? Gabby, raise your hand. Oh, Gabby. Winnie, what do I do next? Where's Evan? Evan, what do I do next?
The numerator also split up for
Is the numerator also what?
like. we stacked up the numerator.
So it factor, so I don't see, so when we factor something, I only see one term in the numerator, right? Or are you talking about the numerator and denominator, so factoring something out of both for those? Here, I don't know if this is helpful, but a lot of times because of the commutative property where 5 times 3 is the same thing as 3 times 5, the order in multiplication doesn't matter. The order for addition doesn't matter either. For subtraction and division, the order does matter. That's where we get a little bit confused. But isn't this based on the commutative property? Couldn't I rewrite this as 16/6 times x to the power of 4 over x times, I guess, y to the power of 6 times z to the power of 2 over z to the power of -2? Is that allowed? Yeah, based on the commutative property, the order doesn't matter, so I can just separate them all like that if I wanted to. So how would I do these in pieces then? Can I simplify this? Is that possible?
Yes,
To what?
8/3.
All right, 8/3. So I'm going to move over here. This is going to give me, I'll use red. So I'm going to get, actually, I'll just write underneath it. I'll write it underneath. So I'm going to get 8/3. What about, let's pick on Natalie. Natalie, can I do anything with this? To the power of what? Yeah, x to the power of 3, yeah. We can either use one of our laws where we subtract the exponent, we just subtract the exponent, or we could expand this and then eliminate. That's the other choice. We'll get the same answer. So that's going to give us x to the power of 3. I agree with you, x to the power of 3. Jacob, where's Jacob? Jacob, anything to do with this? Not really. There's nothing we can combine it to. So let's just combine that to the numerator because it's already positive. How about Adam? Adam, what can I do with this? I agree with you, z to the power of 4. So what you're doing is subtracting you're using our law where you subtract, right? So we have z to the power of 2 minus -2, which will give us z to the power of 4, right? Nice. So there you go. There you go. Actually, I guess I could move this 3. I guess I could move that 3 over. Something like that. What's that, Bryn?
No,
Oh, I didn't hear what you said.
I didn't say anything.
Oh, did you say meow?
When I heard my name.
Okay.
I meowed.
I swore I heard you say something. Or, oh, well. Okay, I want to rewrite nine to the power of 2x so that it has a base of 3. Is that possible? Yes.
It's not about that, but if you have like a fraction, exponents and then that's times the exponent, the whole fraction is, you just.
So you have something like 8 to the power of 1/2 to the power of 1/3.
No. Like fraction.
Okay, so like 1/2 to the power of. Okay, so 3. So what that means based upon this looks a lot like, I'll actually grab it and bring it down. Copy. It looks suspiciously like this one right here. Don't you think?
Oh, okay.
So do you see that the 3 belongs to the numerator and denominator? Okay, cool. Good question. All right, so how do I do this? Yes, Thomas.
Well, first you'll separate the 9 to 2 and 3, so 3 to the power of 2.
All right, so we're going to rewrite that 9. I agree with you. We're going to rewrite that 9 to be 3 to the power of 2. And we still have all that 9 to the power of 2x. Now what?
Now you would use the
The power to the power law,
yeah,
which is
multiply
I multiply to get 3 to the power of
4x.
4x. Nice. Cool. Good job. That is definitely a great way to simplify. All right. Using that information that Thomas helped us find, can I solve for, that's a sloppy 4. Let me just try to clean that up a little bit. I want to solve for 9 to the power of 2x equals 3 to the power of 3x minus 5. What's your name?
I'm Gabby.
Oh, hey, Gabby. Gabby, I called on you and you weren't here, so it was, you got out of being called on. Lucky. Or not lucky. I don't know. We learned through repetition, so you missed an opportunity to get repetition. How do I? You guys want more think time? Okay, Lachlan, how do I do this?
I started with turning the 9 into 3 to the power of 3. And times 2x.
It's 3 to the power of 2.
Oh, yeah, 3 to the power of 2.
Okay,
Times 1 to the 2x.
so I have 3 to the power of 4x equals 3 to the power of 3x minus 5. Okay.
Yeah, and that's all you have to do.
Okay, can you, when you look at this, do you see another step? Is there something else we can do at this point? Lachlan, if I had something like this is just as sidebar here, and I have something like this, I have 5x to the power of 5, 5 to the power of x equals 5 to the power of 3. What does x equal? Yeah. How'd you figure that? That's the only thing it could be, right? If this is my exponent here and this is my exponent, that's the only thing it could be. So couldn't you say then, Lachlan, that once you have the same bases, it implies the exponent's equal? Do you see that we have the same bases? Implying that the exponent's equal. So isn't it also true that we have 4x equals 3x minus 5? Okay, now what, Lachlan? Okay, subtract 3x from both sides. That gives me x equals -5. Huh, there you go. That's the answer. So as soon as we get the same bases, it implies the exponents are the same. Let's look at an example. Let's say, this is actually a true example. This is something I pulled out of another book, but approximately if a rat population is growing under ideal conditions, is left alone under normal conditions, it will grow at a rate of 20% per week. We start with 100 mice or rats. What is an equation for this situation? Now it feels like secondary math 1. What's our equation? Adam? Nice. So we have, in fact, generally speaking, if I have my function, if y equals f of x, and f of x is my function, then my function is going to be f of x, which is my y, equals my f of 0. Adam, what does f of 0 mean? Yeah, that's my 0 term. And then times r, which is my rate of growth to the power of x. That's my equation. So my 0th term is 100. That's what we start with, 100. And then my rate, my common ratio is what? What is it? 1.2. If you ever grow at a rate less, if you grow at a rate of 1, I grow at a rate of 1. So I have $10 today and I'm growing at a rate of 1. So tomorrow I'm going to have $10 the next day. $10 the next day. Nothing changes. If my multiplier is greater than 1, then what happens? Exponential growth. If my multiplier is less than 1, then it is exponential decay. Okay, so if I'm growing at a rate of 20%, it means whatever that baseline is, 100%, I'm growing 20% more than that 100%. Does that make sense why our multiplier is 1.2? Or is that confusing? I don't see anybody responding, so I don't know whether that's confusing or not. If you ever multiply by 1, nothing changes. If you multiply by less than 1, it goes down. If you multiply by something greater than 1, it goes up. So this has to be more than 100%. So we're taking 100%, which is our baseline, and we're growing by 20% more. So it has to be the 100% plus the 20%, which is going to give us that 120% or 1.2. Okay, to the power of x or t or whatever else you want as your variable. So there is our equation. What if I wanted to know, actually, we'll get into this in a second. What if I'll get, so when does the population of rats reach, I don't know, how about 1,000? Let's do 1 million. 1 million. When does the population of rats reach 1 million? Isn't it without any rates? That sounded weird. Okay, it always helps to go back and read your stuff because, yeah, otherwise you get some weird stuff. Did I do that before? No, good. I don't know why I did it the first time. All right, when does the population of rats reach 1,000? How do I figure that out? Yeah, This is my population. What does X represent?
Time.
Time. So I'm going to have 1,000 here, or sorry, a million. I wanted a million. A million here equals 100 times 1.2 to the power of X. How do I solve for X?
First, we divide 100 to both sides.
First, we divide by 100 to both sides. Whenever we multiply by zeros, it's super easy because you just eliminate zeros, right? So that gives me 10. You guys know about that, right? Only with zeros, right? And then that goes away and I'm left with 1.2 to the power of X. Well, now what?
Now you keep the log base 1.2 of both sides.
So there has to be something to undo an exponent. And it is a logarithm. And that's the direction we're going. I'm going to go ahead and finish this because it is that important. So I'm going to do log base what?
1.2.
1.2 to both sides because log base 1.2 of 1.2, those are inverses, they undo each other. And that leaves us with, well, we have to throw that in our calculator. Google is a calculator. Actually, I'm going to use Desmos. I really do like Desmos. And you should get used to Desmos. It's a great resource. So I'm going to type in, if it'll bring me there. So I have log. Do you guys know how to do a base of? Do you know what symbol to use for a base of? To do a subscript?
I just use the keyboard.
Okay, you could use it to do an underscore. If you do an underscore, do you know where an underscore is? Is that minus? It's underneath the minus. So it's shift minus, oops, shift minus. There's my underscore. 1.2. There's my underscore. So I have log base 1.2 of 10,000. How many years is it going to, or sorry, was it years or weeks? How many weeks?
50.517.
How many weeks are in a year?
52.
So it takes a little less than a year. In less than a year, 100 rats will turn into 1 million. Crazy. Under ideal conditions, right? There has to be enough food. There has to be enough space. It can't be any diseases. Rats will grow at that rate. Wow. About approximately, we're going to do these tildes, 50 weeks, under a year. Crazy. All right, so this is really, so we started with exponents and then we're going to logarithms. Now, if we have something like, say, y equals, let's do something like this. If I have the square, if I have x squared equals 25, and then we want to solve for x, what's the inverse of something squared? This square root. You just remember plus or minus, these go away and we're left with x equals what? Plus or minus 5. Okay, so we know that the inverse is, if I have y equals x squared, the inverse is going to be what? What's the inverse of squared? Square root. We're going to do a plus or minus the square root of x. And what happens when we look at these relationships? This, oops. Is y equals x squared. And who remembers inverses? Inverses graphically are always reflections across what? What line? Yeah, x equals y. So it's going to be a reflection across this line right here. So we end up with another graph. I'll use, I don't know about gray, I guess. We'd get something like this for our y equals the square root of x. And this piece here is our y equals minus the square root of x. These graphs are relations. The relation graphically is a reflection across the y equals x, always, always. So let's look at something exponential. We're going too fast, let me know. You guys still copying? So what that means, this is an important connection. What that means is if this is my f of x, and this is my g of x, and I take f of g of x, where one function goes inside of the other function. Do you remember this from last year? Then that's going to give me the square root of x squared, which gives me x. And g of f of x is going to be the square root of x squared, which is going to give me. They undo each other. Inverses undo each other. And we're left with y equals x. Y equals x. We're left with y equals x. That's a really important connection for the direction we're going. Now, hopefully this is a review because I'm going through a lot of stuff really quickly. Okay, so we have this. Here is my exponential function. This is my y equals some base a of x. I don't know what base that is. Now there has to be something that's reflected across it, across this y equals x. And just for, lack of a better word, let's call this a log base a. We'll use this log base a of x. Because these are inverses of each other, then if I take this a to the power of log base a of x, this has to be what? When I take f of g of x, I take one function and I put it inside of the other function, it has to equal what? We did this before up here. When I take a function and I plug it inside of the other function, then I have to get what?
X.
I have to get x. That's what inverses do. Inverses undo each other. So I'm going to take my function and plug it. I'm going to take this side, this and plug it inside. So I should get what?
X.
That should give me x. That should give me x. Now it's also true if we do it the other way, g of f of x, I take f of x and I plug it into g of x. I didn't really label them f of x and g of x, but if I take the other function and I take this function and I plug it into this function, I should get what?
X.
I should get x. I should get x. So I'm going to do that. I have log base a of a to the power of x. That has to be, one more time,
X.
x. These are the first laws of logarithms. We know that they have to be reflections of each other across this y equals x. Our exponential function has to have a horizontal asymptote, which means our logarithmic function has to have a vertical asymptote. Correct. They are just reflections of each other across the y equals x. Now I'm going to try to write down, actually that's all you really have to know. Huh? I guess the trickiest one, the most tricky, is if you have something like this. So let's write some stuff down. If I have if I have 2 to the power of log, so let's simplify this. What if I have log base 2 of 8? How do I simplify that? Is there something I can do to it so that I get this exponent?
Yes.
What?
You can separate the 8.
Yeah, I could get two, how many twos? 2 times, yeah, so that I could rewrite this as log base 2 of 2 to the power of 3. So the answer based upon this law has to be what? Has to be 3. That has to be 3. What if I have log base 3 of 9? What does that have to be?
2.
It has to be 2. I can rewrite the 9 as 3 to the power of 2. So I have log base 3 of 3 to the power of 2. The answer has to be 2. What if I have, this is probably the most tricky for students, if I have log base 3 of 1? How? How did you get that? What did you rewrite this one as? 3 to the power of 0, our 0 exponent rule. We can rewrite that as log base 3 of 3 to the power of 0. So using this law up here, if we just go with our exponent, the answer is 0. Nice, cool. So using these laws, we were able to solve for how long it takes for the mice to increase, rats to increase to 1 million, and it was 50 weeks, about 50 weeks. Right. What about log base 3 of 0? What's that? It is undefined. When is x? This is my x value, right? This is my x value right here. When is x 0? For this graph right here, when is x 0? It's never. We have a vertical asymptote when x equals 0, and we approach it but never reach that. So the answer here is undefined. Undefined. Can this value be negative?
No.
No, there's no x value over here that's negative for this graph. So x cannot be negative and it can't be 0. For the same reason, we did another problem over here. When can y be 0? Never, because there's no y value for this graph that is negative. Cool. All right, moving on. What about, let's do transformations. Do we have enough time for transformations? Transformations. Okay, I'm just getting nervous. There's just a ton of stuff we're covering today. Trying to cover all the important stuff for logarithms. So I have y equals log base 2 of x. That's a graph that looks like this. How do I do a vertical flip?
You make the function negative to the function.
To the function. So that would give me y equals negative log base 2 of x. That would be a graph that looks like I'm messing it like this. Is that right? Does that look right to you?
Yeah.
How would I do a horizontal flip?
You would make the x negative.
To make the x negative. So I have y equals log base 2 of negative x. That would give me a horizontal flip, and we would get something like this. How would I do a vertical shift? I want to move this upward by, I want to move this parent function up, say 5 units. What's this point right here?
0 y.
That is
X is 1.
1 0.
Yeah.
It's 1 0. So if I'm moving it up, if I have y equals log base 2 of x, and then plus or minus, if I want to shift it up, 5. Plus 5. And that's going to give me 1, 2, 3, 4, 5. We have our graph is going to cross this particular point right here. Now, I feel a little uncomfortable leaving it like this. Does anybody else feel uncomfortable about this?
Yeah, well, you should probably,
I don't know whether, I don't know whether that 5 is in the function or to the function. So either put the 5 in front and have y equals 5 plus log base 2 of x, or what?
Parentheses.
Or parentheses. So we know it's to the function and not in the function. We need to make sure we do that. But yeah, all of the same transformations that we did before, they all apply to logarithms as well. Okay. Now there's a couple of notations, and because some of the fancier notation calculators that we have, it's becoming less and less important. But we have this is if I just write, say y equals, if I'm not going to say it, what does this imply? Yeah, this implies base 10. It implies we have y equals log base 10 of x. What if I have y equals ln of x?
E.
Yeah, this implies base e. So y equals log base e of x. What is e?
Euler's number. Euler's number.
Yeah. Is it Euler or Euler?
I know.
It's pronounced Euler. It's spelled Euler, but it's pronounced Euler. It's Euler's number, yeah. And so so E is approximately how much? Does anybody know? It's a number in your calculator.
2.71.
2.71, yeah. And we use it when we compound continuously. It's actually a really important number. And this E has become super important in calculus because there's a really cool relationship that the derivative of e to the x gives you. So that you're going to see this a lot in calculus. You'll also see the ln, this ln of x, you'll see that as well. Both of those are important. So now I want to talk about the other laws of logarithms. And if I'm going too fast, let me know. I don't want to leave anybody behind. So these are the properties of logarithms. Here's the first one. So all of it, just like the laws, how many laws do we have of exponents?
8.
8. All 8 are based upon the definition, right? The definition of an exponent is just if we have repetition using multiplication, then we can combine everything using an exponent. And then mathematicians saw a pattern, and so they came up with the laws. Same thing here. All of this, the definition of a logarithm, what is the definition of a logarithm?
Yeah.
Yeah, it's just an inverse of an exponent. The definition of a logarithm is the inverse. I can't find where we are. The inverse of an exponent. Yeah, it's this idea right here. That's the definition. Now, 3 important properties or 3 important patterns were discovered. And those are important enough that we are going to list those here as well. Now, hopefully you remember this from last year as well. If I have log base, and I can certainly show evidence of these if it's helpful. I do get concerned about time though. How do I expand this? What's this in expanded form? These are just patterns that mathematicians have seen. Thomas.
Log base A of x plus log base A of y.
Yeah, log base A of x plus log base A of y. We have another one, there's just 3. We have log base A of x divided by y.
Log base A of x minus log base A of y.
Yeah, log base A of x minus log base A of y. And the last one, I have number 3 is log base A of x to the power of y.
It's y times log base A of x.
Y times log base A of x. Yep. And it actually makes me feel more, this law makes me feel more comfortable with why it is when we have something like this. I have log base 3 of log base 3 of 9. We rewrite this as log base 3 to the power of 2, log base 3 of 3 to the power of 2. And it always makes me feel more comfortable than just eliminating this and getting 2, because that's sort of an exponent and it feels weird that it's, it feels more comfortable to rewrite it using this law where we move it to the front. So that gives me 2 times log base 3 of 3. And now I substitute in 1 and I get 2, right? If I just substitute, if these are inverses and they undo each other and I have 1 to the power of 2, that of course is not going to give me 2, right? So I like this law. It makes me feel more comfortable with why it is that log base 3 of 3, that they are inverses and they undo each other. That makes me feel so much more comfortable doing it that way. What do you think, Bryn? Or are you comfortable with this?
I think I'm comfortable with that.
Good.
Actually, it's like, okay, yeah, I know what it means.
Awesome. Yeah, I think it really, math just, a lot of it comes, not just math, but any skill. It comes down to feeling more comfortable with it, right? Okay, let's do some examples then using our different properties. Here's our example. I want to expand. I want to expand log base, I'm not going to say. How would I expand? I don't like that 3 at all. I don't like the parentheses. Where's Audrey? Where? Awesome. Audrey, where did you start? What's my base? What kind of logarithm is it? Yeah, I don't know either. There's nothing written here. But there's an implication. It implies that it is a base. Do you know what it is? Yeah, it's 10. If nothing's written, it implies it's log base 10. That's an important idea. If it's not written, it implies that it's a base of 10. All right. So where do we go from here? Damien, what about you? So it's to get x cubed minus 1 cubed. Is that allowed? Or is this x minus 1 times x minus 1 times x minus 1, which means you have to distribute a bunch of stuff and it'll take forever? I want you to consider, Damien, using this law here. If I use this law right here, can you think of a way of expanding this? What about you, Bentley?
You could expand it to log of x squared minus log of x minus 1 to the 3rd.
Nice. Cool. Nate, where's Nate? Nate, what can I do now? Can I expand it anymore? What about using this law right here, Nate? Can you see how I can use this somehow with this? Do you see what I did with the exponent? What did I do to the exponent, Nate? Yeah, just move it to the front. Just move it to the front. All right, so how would that help me expand this? What can I do to this exponent, Nate? Can I just move it to the front? And then take this exponent and move it to the front? Isn't that what this law says to do? Just move it to the front, okay. So let's do that here as well. So that's gonna give me 2 times log base 10 of x minus 3 times log base 10 of x minus 1. Can I expand this anymore? We can't use the second law to expand this? No, because it's not, this isn't division or multiplication, right? So I'm stuck. I can't do anything more. That is my answer right here. That is my answer. I'm getting nervous. I'm running out of time. What should I? Okay, so because of lack of time, I'm going to skip some stuff. I'm going to move on to the change of base formula. Change. Sloppy. Change of base formula. This is if I have log base anything of x, I can rewrite this as log base something else of x over that same new base of a. We can do that with log base 10 or ln or anything else. In fact, this, I didn't have subset in my calculator when I was your age. So the only way to figure out like a log base 2 of something was by rewriting this as, I don't know, log base 10 of x over log base 10 of a, or ln of x over ln of a. It's all the same stuff. But I did not have the same option. We didn't have subsets. So you had to use the change of base formula to figure out anything that was not ln or base 10. This is just, it's called change of base formula. So if I wanted to know log base 2 of 5, if your calculator doesn't have a log base 2, we would have to use a change of base formula. So I'd have to rewrite this how? What if your calculator, in fact, let's go to Desmos calculator. Oh, actually Desmos allows me to do a subset. What if let's go to, I'm just going to type in calculator, calculator. Here it says log, but that implies it's log base what? 10. Here I have ln, which means what? So do you see I don't have a log base 2? Since I don't have a log base 2, then how would I rewrite this for my primitive calculator? Bryn.
Log base 10 of 2 divided by log base 10 of 5.
Is that right?
Is it the other way around?
It's the other way around. Do you see that?
Oh, yeah.
You see that the subset is in the denominator?
Oh, yeah.
Subset's in the denominator. No problem. No problem. Bryn, this is the safe time to make a mistake because it's not a test. So it's log base 10 of 5 over log base 10 of 2. Or what if I use ln?
Same, but instead of log, ln.
Yep, that will give me the same answer. In fact, log base 5, so let's do ln of 5 over ln of 2. I'm going to do, in parentheses, ln of 5, in parentheses, divided by ln of 2. And it should give me the same answer, 2.32, as if I go to Desmos and I type in log base 2 of 5. Did that give me the same answer? 2.3219, 2.3219, is that the same? Yeah. So change of base formula. There are some other applications where things get really tricky with your math. And so that's using change of base formula can be helpful. All right. What is your homework for tonight? Which one? 1.5. Awesome. Yes, sir, Bentley.
Which one did you take quizzes you did in the past?